Welcome to PyData Global 2021. This is Laune Saule speaking, and I'll be your session chair for today. First speaker will be Antoni Baum, taking us through cutting-edge hyperparameter tuning made simple with RayTune. And just a brief summary of who Antoni is. Antoni is a computer science, data science, and video game modding enthusiast, and at heart, and he holds a BSc in computer science and econometrics, and currently a student at AGH, an MSc student. Yes. If you want to know more about Antoni, you can go through our schedule on our website. You'll get his profile, and you'll know more. There are links in there to connect with him after this. So at this time, without further ado, I will give the chance to you, Antoni, to share what you have with everyone.
Thank you for the introduction. So today I'll be talking about RayTune and how it makes distributed hyperparameter optimization simple. So just to add to who I am mainly here as a software engineer in Aniscale's machine learning team, but I am also a computer science and econometric master student, and I have been involved in various open source projects over the years. So what we'll be talking about today. So first, I will give a bit of background on what is Ray and what is RayTune. Then I will talk about the challenges of hyperparameter optimization, how those challenges can be solved through both cutting-edge HPO algorithms and distributed HPO, and how Ray allows us to use both. And at the end, I will give a quick example of how to use our sklearn-wrapper for RayTune. So a little bit of background on Ray. What is Ray? Ray is a project that aims to make distributed computing simple and universal. It has been started at the Berkeley Rice Lab and then became an open source project. And since has been developed by Aniscale, which aims to create a platform to provide the best Ray experience possible. Over the years, the project has grown significantly. Right now, we have over 500 users and contributors from a huge number of companies. This is just a selection of them. What are people using Ray for? So for example, Ant is developing Ray on over 200,000 cores for recommendation, fraud prediction, online learning. Amazon has been using Ray to increase throughput of their data processing to over 1 petabyte per hour, while reducing costs by over 90% compared to their previous solution. And Uber uses XGBoost on Ray and Horobot on Ray for most of their machine learning tasks. So Ray is a library for Python, Java, and C++ that provides a universal framework for distributed computing, APIs and primitives that allows developers to easily scale up any of their compute-intensive workloads from a single node to an entire cluster. Ray can be run anywhere. It can be run in a cloud on AWS, Azure, Google Cloud. It can be run on Kubernetes, or it can be run on an on-prem cluster of machines. There are no code changes required between running a Ray program on a single node or on any distributed cluster. Let me quickly showcase those programming APIs that I have been talking about. So here we have a simple example of a very trivial Ray workload. Ray provides both tasks and actors. Tasks are the equivalent of functions, and actors are equivalent of classes. Tasks are stateless, and actors are stateful. We can very easily turn a Python function to a Ray task by using the Ray remote decorator. And this is not showcased in the example, but it is also possible to specify various resource requirements that our task or actor will require during its operation. And thanks to that, it will be able to take advantage of resource our scheduling that Ray uses. Now that we have our task, we can invoke it using the remote method, which will immediately return an object reference, or a future in other words. And it will create a task that will be executed on a Ray cluster that we are connected to. Then we can use RayGet to receive the result of that task. And it is important to note that calling a remote task or a method of a remote actor does not block. So in the second part of the example, we execute slow function 4 times in parallel. It will the tasks will be scheduled on the cluster, and we can return the results once the computation has been complete. So based on those APIs and those primitives, Ray has, as a project, has developed several libraries providing support for different machine learning use cases. For example, we have Ray SGD, soon to be renamed Ray Tune, that allows for deep learning training on a cluster. We have RLib, one of the most advanced and extensive reinforcement learning libraries. And we also have created RayServe, which takes care of model serving at a scale. On this talk, we'll be focusing on Tune, which handles hyperparameter tuning. So RayTune is our solution for distributed hyperparameter optimization. It provides efficient cutting-edge HPO algorithms, and it distributes and coordinates parallel trials in a fault-tolerant and elastic manner. Because RayTune is running on Ray, it can take advantage of Ray features such as auto-scaling, which means that it can request new nodes to be added as resource requirements increase. And it can also bring down nodes once they are not necessary anymore. Thanks to all of those features, as well as overall simplicity, RayTune saves you time and cost every step of hyperparameter optimization. So this is a benchmark that Uber has run on over 2 weeks of production data, and compared to their previous in-house solution, Ray has allowed for over 2 times efficiency improvement in terms of GPU and CPU hours. But before we can truly talk about how RayTune makes hyperparameter optimization simple, we should first set some context about what hyperparameters and hyperparameter optimization or tuning is. So this will be just a brief introduction for those who may not be familiar with the term. When we have a machine learning model, it learns a set of parameters during training. But there are also such parameters that are set before training, and we call those hyperparameters. For example, this may be the number of trees in an XGBoost model, or it can be the number of layers and the kind of layers and the number of neurons in a layer in a deep learning model. With more complex model, the number of hyperparameters can grow very large, resulting in very complex and very diverse search spaces. Furthermore, it is possible to go one step beyond and not only consider the hyperparameters of a model itself, but also consider the hyperparameters of an entire data processing pipeline with an estimator at the end, or even consider the choice of the steps in a pipeline as a hyperparameter itself. Here is a simple example of a pipeline with an XGBoost at the end, and an imputer, a categorical encoder, and under oversampler for imbalanced data. As you can see, the choice of all of those steps and the choice of hyperparameters for each of those steps results in a very large hyperparameter search space, which can be challenging to evaluate on a single node efficiently. HPO, the main challenge of hyperparameter optimization is that it's very time consuming, because the only way we can learn whether the selected combination of hyperparameters gives a good result is by fitting the model. And that can take seconds, but that can also take days, depending on the use case. There is also a large number of combinations that we have to evaluate before we can find such combinations that give good results. On the other hand, we can turn to parallel computing for reducing the time needed, but that will incur additional costs in terms of compute. So how can RayTune help with reducing that cost and time? RayTune provides efficient algorithms that minimize the time necessary to find such combinations of hyperparameters that give good results. And it efficiently orchestrates running the distributed trials on a cluster. And finally, it provides easy-to-use APIs. Furthermore, the same RayTune code can be run on both a single node or on a cluster. And because it is possible for the user to specify their own objective function, it is virtually compatible with every machine learning library. So what sort of algorithm is RayTune providing? We have over 15 algorithms that are natively provided or integrated from other libraries, and it is easy to swap them out with minimal code changes. Let me give you a quick tour. So the simplest way to evaluate hyperparameters is to use exhaustive, also known as grid, or random search. In terms of grid search, we simply try out every possible combination of hyperparameters. And in terms of random search, we just sample the hyperparameter distributions randomly. And because every trial is independent from each other, it's very easy to parallelize and easy to implement. But most of the times it is quite inefficient and compute intensive, as the information from the previous trials is not used for choosing the combination in the next trial. Here we can turn to Bayesian optimization, which in its simplest explanation uses the results, the information from previous evaluated trials to decide which trial to try next. This usually involves fitting a surrogate function and using that to choose the next combination to try. Bayesian optimization is inherently sequential because it requires the information from previous trials. However, there have been seen some advances that allow parallelization of different types of Bayesian optimization. Some popular libraries that implement Bayesian optimization are HyperOpt, Optuna, scikit-optimize, and Nevergrad, and there are, of course, many more. All of those libraries here have been integrated into RayTune. Aside from choosing what configurations to evaluate, we can also improve efficiency of our tuning by using advanced scheduling. This means that we use the intermediate results of a trial, such as epochs, trees, or samples, to prune underperforming trials, saving time and computing resources. There are various algorithms for that, such as median stopping, hyperband, or ASHA, and they can be sometimes combined with Bayesian optimization. The figure here showcases the successive halving algorithm, where in each run, half of the worst performing trials are terminated, and the other half is let to run until their resources are exhausted. In practical terms, that would mean that more combinations can be tried without having to evaluate them fully. Another type of advanced scheduling is population-based training. It is mainly intended for schedule parameters such as learning rate in neural networks. And we evaluate a population in parallel, terminate lowest performers, and then copy the weights of best performing trials and mutate them. This is a type of an evolutionary algorithm, and it can be quite tricky to implement on your own. Thankfully, RayTune provides an implementation. There are also some other advanced sampling algorithms that have been integrated into RayTune, such as blend search, which takes into account the execution time of each combination and progressively trying more expensive combinations. So for example, it may try with very small XGBoost models composed of only a couple of trees and progressively move to bigger models which take more time to evaluate. We also provide an integration with heteroscedastic evolutionary Bayesian optimization, which combines Bayesian optimization with evolutionary algorithms. This algorithm has won the New York IPS 2020 Black Box Optimization Competition. And we provide an integration for BOHB, which combines Bayesian optimization with hyperband, meaning it can make informed decision based on partial results and terminate underperforming trials. So let's review what we have talked about so far. There are various HPO algorithms, and there is a huge trend of going parallel as the evaluation times of models increase. More advanced algorithms are often hard to implement, and even more so in a distributed setting. All of the different libraries that implement those HPO algorithms have their different APIs and different functionality. However, RayTune implements and integrates with all of those algorithms and their parent libraries, and it also allows you to bring your own algorithms. It allows the user to swap out the different algorithms very easily and take benefit from a unified API. Now that we know what sort of requirements HPO algorithms may have, we can think about what sort of architecture we will require in order to efficiently conduct distributed hyperparameter optimization. So we definitely require granular control over when to start, pause, early stop, and restore or mutate each trial at specific iterations with little overhead. We require a master worker architecture that centralizes decision-making so that the orchestrator has access to the information from all the trials. We have a sampler which provides combinations to evaluate and a scheduler that decides which trials to stop, start, and pause. And since we are talking about the distributed hyperparameter optimization, we need to have elasticity and fault tolerance. So how does RayTune implement all of those architecture requirements? First, the user provides their own training function. This can be any calculation using any machine learning library. By using tune report, the metrics are reported back to the orchestrator, which launches worker processes. Those worker processes each have one trial, and one trial corresponds to one combination of hyperparameters. Because we are running this in a distributed setting, those worker processes can be scheduled on both the head node and worker node as resources permit. The worker processes report back metrics to the orchestrator, which keeps track of all of the trial's progress. And based on those metrics, the orchestrator may stop, pause, or mutate trials, and it can launch new trials when resources become available, in other terms, when one of the worker processes terminates. Furthermore, in order to provide fault tolerance, the orchestrator also manages checkpoint state. And in case one of the worker processes crashes, the orchestrator can load the checkpoint from cloud storage and restore the training from back when it stopped. So let's quickly review what we have talked about. What makes RayTune special? First, it provides various types of efficient HPO algorithms, and it distributes and coordinates parallel trials in a fault-tolerant and elastic manner. It is well integrated with the ML ecosystem. So, as I have mentioned before, it is the user has to create their own training function. However, in order to simplify things and with how popular scikit-learn APIs are, and for a good reason, they are very easy and pleasant to use, we have created a scikit-learn wrapper for RayTune. We wanted it to be a drop-in replacement for the scikit-learn model selections module, which provides randomized search CV and grid search CV. And we wanted it to provide a familiar and simple API for advanced distributed HPO. And here is our project page. So this is an example of how we would use scikit-learn model selection with grid search cross-validation. And the one thing about scikit-learn implementations is that they can only be run on a single machine. However, by using tune-sklearn, it is possible to, just with 2 lines of code changed, harness the power of an entire array cluster and use all of the resources available throughout the entire cluster. Furthermore, tune-search CV allows you to choose all of the different optimizations, algorithms, and schedulers present in RayTune. And it allows you to specify the resource requirements for your models. So here is a quick demo of how tune-sklearn can be used. We are using a driver safety prediction data set, which has around 600,000 rows and 50 columns. It uses a cluster that has been started before through Ray Cluster Launcher, which composes 5 nodes, each with 8 CPUs. And we are using a Jupyter notebook that runs on the head node. So first, we will connect to our Ray cluster by using Ray init. And we can see how many CPU resources we have. This is the scikit-learn code, randomized search CV, but we can very easily turn it into tune search CV. We replace the SciPy distributions with tune distributions for hyperparameters. And we simply replace randomized search CV with tune search CV. And we can choose how many trials we want to run in parallel. And we can also take advantage of early stopping as described before. And just like that, we get our result, and we can access the entire history of optimization through the analysis object returned by tune search CV. And we can also plot the cumulative maximum score over time. Finally, we disconnect from the Ray cluster. Thank you. This concludes my talk. Let's keep in touch. Here are some links to our Ray website, our discussion forum, and our Slack, and to the GitHub page for tune-sklearn. I am happy to take any questions you might have now.
Thank you so much, Antoni. Here we have a question from, I don't know if I'm going to pronounce your name correctly, Anatole. So Anatole asks, do you provide classical parameter grids for most popular algorithms?
We do not do that. However, there is a project that is being conducted right now that eventually aims to allow for us to suggest which combination of search algorithms and parameter grids would be most suitable for a given task. However, this will probably take some time before it is complete. That being said, there are many AutoML libraries that are based on RayTune or have support for RayTune, like Ludwig, which provide pre-made parameter grids.
Okay, thank you so much. I think we have another question here. Mm-hmm. Oh, it says, how does Ray work together with MLflow? Mm-hmm. I see certain overlap, but not fully. Yes, but not fully.
Right.
Yes.
So Ray by itself only provides APIs and primitives for other libraries to be built upon. However, RayTune has an integration with MLflow, a callback that reports the results to MLflow. So you can maintain a unified history of the optimization with MLflow. We also support weights and biases. We also support TensorBoard, and it is possible for you to write your own callbacks for any bookkeeping solution you may require.
Okay, I hope Guido got his or her answer. We have another question from V. V asked, V says, I use Dockerized trainers and DVC metrics. How hard do you think will be integrating to Ray?
That's a very good question. I would have to probably answer that offline once I know more about your use case. So let's connect on Slack if possible.
Okay, V, I hope you heard that. We'll get your answer on Slack. And Nick asks, if a single machine with multiple cores or GPUs is powerful enough, does Ray offer any advantage, or it is mainly for setting where you need a cluster?
Mm-hmm. So RayTune provides a unified API for various different search algorithms, which allows you to easily see which one is the best for your use case. And at least compared to scikit-learn, it allows you to specify resource requirements for each trial with a huge degree of flexibility. As far as I understand, scikit-learn doesn't really support GPU training. However, with RayTune, it is possible for you to define how many GPUs each trial should use, and that will ensure that the trials run without any slowdowns or interruptions.
Okay. If there are no more further questions, I think we've come to the end of your talk. And I'm certain that all those who attended have really learned a lot. And just a reminder to everyone attending, this recording will be available on our YouTube channel, and we also have Slack in case you can't ask anything now, but you want to connect with Antoni later. You can get his profile from our website and connect with him on GitHub and LinkedIn. Thank you so much, Antoni.
Thank you all.